Okay, this is 3.15, and this is going to be about the use of matrices and walks in graphs. So I'd like everybody to pause this for a second after you got and look at this video. What is a random walk? It's in 3.15.0. Okay, now that you've looked at what a random walk is, one of our key concepts here is that patterns that emerge from randomness allow us to approximate future conditions of a model. So because randomness is often how future works, the patterns that emerge allow us to see things that may or may not happen in the future and what it's going to look like for that model. Your theory of knowledge connection is important to consider the impact of culture of the individual knower. However, it seems at first glance that mathematics is immune from cultural biases. Think about this. Is this statement accurate? Is this immunity a key factor in creating mathematical authority in regard to knowledge validity? Or, on the contrary, do you believe mathematics is also influenced by culture? The knowledge question that it poses, is it possible to abstract knowledge from the culture in which it was produced? Things to think about, discuss. Okay, on to 3.15, adjacency tables. So here we have a graph. It's got 6 vertices and a bunch of edges. Make an ordered list containing all the edges in the graph. Well, if I wanted to make an ordered list, be something like AF, AB, AD, AE. That's all my A's. I guess they're not quite ordered, but I'm gonna go to B. BA is really already included, but I'm gonna put it there again. BC, BD, BF. So those are duplicates. Nothing else is duplicated yet. I'm listing them there because it's going to help for my adjacency table. So it says reflect on the order. I'm ordering them based on what's leaving, going A, B, C, D, E, C, B. I've got that. C, D, and C, E. And I've got D, A. That's, that one's here. D, B. If I was just listing edges, I probably wouldn't list duplicates. So I reflect on my order. D, E, and D, F. And I've got E, A, that's a duplicate. EC is a duplicate. ED is a duplicate. This is EC. And then I think all the Fs are already listed. FA, FB, and FD. And again, I wouldn't list the duplicates, but that leads us into something called an adjacency table. So an adjacency table takes the connections between things. So notice I've got from my list BA. There's exactly one edge connecting B to A and A to B. There's my duplicates. A to D and D to A. Let's do So this is an adjacency table for that graph. If I look here, AF, that shows up right here. Let's change the color again. AF shows up there and there. AE, and you can see this adjacency table, how it matches the graph up here. And yes, we don't have any twos because there's no doubles, like we did see some in previous ones. I don't have two edges connecting any of the graphs, like say this. I don't have any between, say, B and B, all of those, because I don't have any loops like that around B. Okay. We look down here. There's zeros on all the ones that match up D to D, etc. So that is an adjacency table. Works right about like that. Create an adjacency table for this. Okay. Well, one of the keys here, I need to put all my vertices on both rows and columns. So an adjacency table is a giant matrix. Should be a square matrix. Let's make a nicer E than that. So from A to A, there are none. From A to B, there's two. From A to C, there's one. And I'm just going to put those together. From A to D, there are not any, and there's not any from A to E. Okay, from B to A, there's two. From B to C, from B to B, there's zero. From B to C, there's zero. From B to D, there's one. And put that in. I guess I probably don't need to. And from B to E, there's one. From C to A, there's one. From C to B, there's zero. From C to C, there is one. From C to D, there is one. There's zero from C to E. From D to A, there is zero. From D to B, there's one. D to C, there's one. D to D, there is zero. D to E, there is two. E to A is zero. E to B is one. E to C is zero. E to D is two. E to E is zero. And there's our adjacency table, which we can see they got the same thing we did. Wait, C to C, there's two. Oh, sorry, my bad. All loops are considered two because it's coming and going. So this little loop here, that'll circle here in red, that little loop comes into and goes out of C. So that, when I look at, should be considered, this should be crossed out. That should be a two. I forgot about that from the previous year. But otherwise, the adjacency table is exactly what we created. Okay, important. The degree of a vertex can be found by finding the sum of the values in its row or column of the adjacency table. They should be the same. The sum of all the values in the adjacency table of an undirected graph is equal to twice the number of edges in the corresponding graph. A loop is counted as two to maintain this relationship within the adjacency table. Note that in other sources you may find a different approach that represents loops in the adjacency matrix. Some authors prefer to count a loop as one edge and enter one in the diagonal, Both approaches can be used, but it's important to be consistent. So now we have create the graph from an adjacency table. So I've got A, B, C, and D. Remember, it's not about location for these vertices, it's just about connections. So A to A is 0, A to B is 1, A to C is 1, and A to D is 1. B to A is 1, B to B is 0, B to C is 1, and B to D is 1. This might be a complete graph. C to A is 1, C to B is 1, C to D is 1, C to C is 0. Yep, that's a complete graph. Let's see what theirs looks. They got roughly the same thing. So, symmetry along the diagonal. So consider the diagonals in the adjacency table formed by the cells AA, BB, CC, etc. So we got 0 on all of these. What does that tell me? This is called the leading diagonal. Recall that the adjacency table on the left was from a simple graph shown in the important box above. What values is in its leading diagonal? So these are all zeros. What does that tell me? Up here we had a multigraph that didn't have it all. They weren't all zeros. There's a 2. The 2 is a loop. This one, the all zeros, tells me there are no loops. It asks you how the values on the right of the leading diagonal compare with the values on the left. That's these. If you'll notice there's symmetry right here. Those are the same. This is going to be true for any undirected graph. This goes with this. This one goes with this one. It's all the way across. So we've got all kinds of symmetry there. Important. In a simple graph, all the values on the leading diagonal will be 0. Simple means no loops. All other entries in the adjacency table and no duplicate edges. All entries in the adjacency table will either be 1 or 0. All adjacency tables of undirected graphs are symmetric about the leading diagonal. That's not true for directed. We'll get to that in a second. Note the answer for example 2 was a complete graph. Okay, remembering back to terminology from 3.14. Complete graph, all edges and diagonals or all vertices connect to all other vertices with a single edge. Now, if we're doing a directed graph, um, recall a little bit of things. I sub j is ith row, jth column. So this is matrix notation. A23 would mean second row, third column. Okay. So the value important, the value Aij in the adjacency table for a directed graph is the number of edges that allow you to travel from I to J. So construct the adjacency table for the graph shown above. Well, again, A through F, D, E, F. So allow me to travel from row A to B, 1. A to A is 0. Row A to C is 0. A to D is 1. A to E is 0. And A to F is 0. I'm going to double check that in a second that I did this correctly, but I believe that's right. Then I look at B. The only one going out of B is to F. Yes, that is correct. So the rest of these are zeros. I'll get the ones coming into B in the column when they come out of C. C does not go to A. C does go to B. C doesn't go to C. C goes not to D. C goes to E and not to F. D goes to B, goes to C, and it goes to F. E goes to A. He's got an edge going to A and one going to D, and zeros for everything else. F goes just to A and nothing else that it goes to. So if I scroll down, we can see that that matches my adjacency table here. And it's all about where it's going. Okay, that's the key. Goes from A to B, from A to D, from E to A, from F to A. So that's for directed graphs. Now, what about weighted graphs? An adjacency table is not necessarily symmetric across the leading diagonal. Okay, that's important. Now for a weighted graph, the adjacency table, we just put the weights in them. Okay. They don't really have any with duplicates in here. So common examples used for the weighted edges in the weighted adjacency tables include cost, distance, and time. Recall that in the video from 3.14.0 that Euler's development of graph theory originated from his desire to solve the seven bridges of Königsberg problem. The city of Königsberg was mostly destroyed by extensive bombing during World War II. It was rebuilt and renamed Kaliningrad by the Soviet Union and is now part of Russia. You can still see some of the original bridges in online maps. Someone were to ask you to list the cities that no longer exist, which ones would you include? Troy, Inc., or other ancient cities? Okay, there's all kinds of ancient cities that don't exist, but this is one that kind of does. Okay, but it's interesting to note that it was destroyed in World War II and rebuilt by the Soviet Union. Okay, now it's time to talk about walks. Okay. A walk is essentially a trip through a graph. So it's a sequence of connected edges. For the graph shown above, find the number of walks of length 2 between vertex A and D. So AD is not length 2. That's not a walk. But ABD, actually I should do it like this, ABBD is a walk of length 2. AFD is a walk of length 2 between A and D. AED is a walk of length 2, meaning it went 2 edges. There's no more length 2 walks, but a length 3 walk would be AE, EC, ED, or CD. So that's a walk of length 3. There's walks of length 3. You could have a walk of length 12. You might end up going through D before you get there, but it's all about ending at D, so I suppose you could do that. But a walk is just a sequence of connected edges. So we did our length 2. Now, consider this adjacency table. By choosing an appropriate method, find the number of walks between A and D that are length 3. So this is the adjacency table. They're like AE, EC, CD. I could do it from the adjacency table. I could go A to B. A to B, that's part 1. Then I go from B and go to C. And I can go from C to D. That's 3. So I went A to B. I suppose I could have went B to C there. C to D here. However you want to do that. I need to make sure that everything connects. Um, the other method you can do, which is really nice, is you can input all your values into a graphing calculator, GDC, as a 6x6 matrix. Find A squared, and then look at A 4, 1. Okay, that does matter. I think it matters. I have to remember for sure. So let's try this. We're going to put our adjacency matrix in a graphing calculator. And this is the easiest way to do this. Okay? So I come over here to this key next to the 9, pick matrix. I need it to be 6 and 3, or 6 and 6. And I just enter my adjacency matrix. This takes a little bit of time. But if it asks you for the number of walks, I found 1. But if I want to know the total number of triple of 3 of walks of length 3, that's how you say it, I can put it into this adjacency matrix. Oh no, this must be, I think they're having me do walks of length 2. Keep in mind this is an undirected graph, so now it tells me to have it A, so I'm going to store. That's control variable stow, and I'm just going to say A. Now it asks me to do A squared. So I just type in A squared. And I'm looking at this value right here. A41. I guess A14 ends up being the same. Because this is not directed, it probably doesn't matter. But yeah, this is symmetric along the diagonal. But if it was directed, it's important that you note that it would be A41 going from row to where I'm going column. So it says that there are three. That's the value. It's simply there's three of them. Okay, if we look at our graph, we can actually go find those three. This is walks of length 2. So we look up here, and I think we actually found the three before. So, example 2. Find the number of walks from B to E that are length 6. Okay. Well, I've got my matrix. Already made it. A to the 6th. Whoa. This is how many different ways I can get a walk of length 6 from B to E. Remember that this is A, B, this is column E. 446 ways. Bet you didn't see that coming. So this is where the adjacency matrices become really, really useful. When your walks are length 2, not that big of a deal. When they're length 6, really big deal. So this one has you create the adjacency table. And it's a complete graph. And then find the number of walks of length 3 or less between C and D. So 3 or less, I create the adjacency table. I do A2, I do A3. A1 is shown in the adjacency table. So I simply take, I'm looking at C to D. So these are the columns. So let's take a look at that adjacency table. Oops, sorry. I was looking at the wrong screen when I was doing this. Example 3 here. Here's my graph. We create the adjacency table, and then we do 3 or less. So that's A1, A2, and A3, and it's from C to D. That's this, and that, those values, and that gives me 10. 10 different walks of 3 or less. Okay, final thing we need to talk about is a random walk. So this is kind of an interesting little thing. It's randomly choosing where it's going. And it can go either way. It can go any of the 4 directions. And then it's plotting it. It's running out. If I reset, notice it's going somewhere different. So it can go kind of, I think it's basically the graph above, but then it's just shooting off in all kinds of directions. In the applet shown above, by pressing the reset button, you start over and you watch the dot move around the screen. If it is too fast, you can slow it down. So that's your grid. Okay. How does the computer decide where to go? It's a random selection. So here we have our graph again. Okay, when calculating probabilities for random walks, there will be an equal probability of leaving a vertex via any available edge. So leaving A, there's 4 edges, 1/4 chance of going on each one. Leaving E, there's only 3, so that's 1/3. In directed graphs, you only count the ones going away from the edge, as the probability is not that. So transition matrix, this goes way back to matrices, contains the probabilities of moving from one vertex to another. Create a transition matrix for the graph shown above. Okay? And this is all the probabilities. Those are the 4 edges A could go to with 1/4 probability each. 0.25. 0.3 with the dot above it, I guess, is 0.3 repeating. That's a new one for me. Not a bar. Same idea. So we get this matrix, and they put it in as a matrix. Now it says do it for the directed graph. Well, you get, there's only 2 edges now leaving A, so they're 50%. Only 1 coming into B, or 1 leaving B, that's F. Okay, so these are all about leaving. And that's how we get our, if we want a random walk of 3 on that, what's the probability of ending up each place? So it says, here we just wrote our matrix. Now, find the probability the random walk begins at vertex A and ends at vertex E. So begins at A and ends at B, at E. So a random walk of length 3, here's my adjacency table, or my, using the wrong term. It's my transition matrix. My transition matrix for the weighted graph is here. If I want length 3 to get from, the question asked me A to E, I'm going to look at T cubed, column or row A, column E, 0.0833. Okay, this is where being directed matters, that I started at A and went to E. It is not, this one would be started at E. That's, the blue one is E2A. Okay? That's where it matters, row, column. Okay? You can check that by what did they do? 1/2. They created a path. 1/2, 1/3, 1/2. Equals 1/12, which is what you got. This one apparently was only one with 3. The transition matrix becomes a lot more helpful if there's multiple walks of length 3 that could get you from A to E. This one only had 1, so yes, your results match up. 1/12 is 0.0833. Okay, that is 3.15.